J. Littleton here, and welcome back to the channel. Today, we're exploring some of the most extreme objects in the cosmos, neutron stars. These aren't just dense, they're incomprehensibly, mind-bendingly dense. A neutron star the size of a city contains more mass than our entire sun. A teaspoon of neutron star material would weigh as much as Mount Everest. But that's just the beginning. Neutron stars spin hundreds of times per second. Their magnetic fields are strong enough to tear apart matter from light years away. They produce some of the universe's most violent phenomena. And they're laboratories where physics breaks down and reality becomes extreme beyond our comprehension. We've observed neutron stars. We've detected their radiation. We've even measured their surface gravity with stunning precision. And what we've discovered is forcing us to reconsider what's possible at the extremes of physical reality. If you love extreme physics, cosmic violence, and objects that challenge everything we know about matter itself, this is for you. Let's dive in. Imagine standing on the surface of an object so dense that a single teaspoon of its material weighs 6 billion tons. A teaspoon. That's the mass of Mount Everest, compressed into a volume the size of a sugar cube. Now imagine that object spinning, not slowly, hundreds of times per second. A city-sized sphere rotating so rapidly that its surface moves at a significant fraction of light speed. The centrifugal forces would be apocalyptic. Now imagine that object's magnetic field, so intense it could kill you from thousands of kilometers away. Powerful enough to strip atoms from matter, to accelerate particles to relativistic speeds, to create electromagnetic phenomena that outshine billion-star galaxies. This is a neutron star, one of the universe's most extreme objects. The remnant left when a massive star dies catastrophically. The compressed core of stellar death, packed so densely that matter itself transforms into something alien and bizarre. For decades, neutron stars were theoretical. We calculated they should exist. We couldn't imagine how we'd ever observe them. Then, in 1967, something astonishing happened. A young astronomer named Jocelyn Bell detected radio pulses arriving from space with incredible regularity. The pulses were so regular, so precise, that she initially wondered if they were artificial, messages from aliens. The signal was labeled LGM-1, Little Green Men. But it wasn't aliens. It was the first confirmed neutron star, a pulsar, beaming radiation across space like a cosmic lighthouse. Since then, we've discovered thousands of neutron stars. We've observed them colliding and merging. We've detected them in binary systems tearing apart companion stars. We've measured their properties with stunning precision. And what we've learned forces us to confront physics at its absolute extremes. Prepare yourselves. We begin. To understand neutron stars, we must first understand how they form. Stellar death. Most stars end their lives gently. Our Sun, for instance, will eventually shed its outer layers and leave behind a white dwarf, a cold, dense stellar remnant the size of Earth but with the Sun's mass. A white dwarf is extraordinarily dense by everyday standards. A teaspoon of white dwarf material weighs millions of tons. But some stars are different. Massive stars, stars beginning with 30, 50, or even 100 times the Sun's mass, end their lives violently. These massive stars burn through their fuel rapidly. They live fast and die young, measured in millions of years rather than billions. When they exhaust their nuclear fuel, their cores collapse catastrophically. The collapse happens in seconds. The star's core, no longer supported by radiation pressure from ongoing nuclear fusion, implodes under its own gravity. Electrons are forced into protons, creating neutrons. What was once city-sized becomes kilometer-sized. What was kilometer-sized becomes meters. The compression is apocalyptic. At a certain critical density, something remarkable happens. The neutrons themselves begin resisting further compression. Quantum mechanics forbids packing neutrons more densely than a certain threshold. Neutron degeneracy pressure, the quantum resistance of neutrons to compression, halts the collapse. The result is a neutron star, an object so dense that gravity has transformed stellar matter into something alien. Protons and electrons have merged into neutrons. Nuclear forces dominate over electromagnetic forces. The object is essentially a single, incomprehensibly large atomic nucleus. This happens in seconds. One moment, you have a star perhaps 20 times more massive than our Sun, burning steadily in space. Moments later, the star explodes in a supernova, dispersing its outer layers into space. And at the heart of the explosion, a neutron star is born. The density is incomprehensible. A neutron star typically has a mass of about 1.4 solar masses, equivalent to our Sun's entire mass, compressed into a sphere perhaps 20 kilometers across. That's a city-sized object weighing as much as the Sun. If you attempted to compress our Sun into a neutron star, its surface gravity would be so extreme that escape velocity would be about 1/3 of light speed. Objects would be crushed by gravity into neutron star material. The space-time curvature near the surface would be severe enough that general relativity becomes essential for accurate calculations. In 1934, just 2 years after the neutron was discovered, astronomers Fritz Zwicky and Walter Baade predicted that massive star deaths would create neutron stars. They imagined extraordinarily dense objects with extreme properties. Physicists dismissed the prediction as wild speculation. But in 1967, Jocelyn Bell's discovery proved them right. Neutron stars were real. Since Bell's discovery, we've identified thousands of neutron stars. Most are pulsars, rotating neutron stars that beam radiation across space. Their rotation sweeps beams of radiation towards Earth like a lighthouse, producing regular pulses. But the evidence forces us to confront something uncomfortable. Neutron stars are even more extreme than early predictions suggested. They're laboratories where physics transforms, where matter itself becomes alien, where extremes reach levels we struggle to comprehend. Scientists discovered that neutron stars rotate at mind-bending speeds. Some spin only once per few seconds. Others spin hundreds of times per second. The fastest known pulsar, PSR B1937+21, rotates 716 times per second. Think about that. A city-sized sphere spinning 716 times every second. The surface velocity at the equator approaches a significant fraction of light speed. Centrifugal forces are apocalyptic, yet the object holds together, compressed by its own intense gravity. These rapid rotations create something extraordinary. Pulsars beam radiation across space. A neutron star's intense magnetic field funnels charged particles towards the poles. As particles spiral down magnetic field lines, they accelerate and emit radiation. Beams of intense radiation emanate from the poles. As the neutron star rotates, these beams sweep across space.
When a beam points towards Earth, we detect a pulse. From our perspective, the neutron star appears to pulse on and off, thousands of pulses per second for the fastest pulsars. Scientists discovered that pulsar timing is incredibly precise. The fastest pulsars maintain timing accuracy comparable to atomic clocks. This precision revealed something remarkable. We can use pulsars to detect gravitational waves, black hole systems, and other exotic cosmic phenomena. In 1974, scientists using pulsars made a discovery that changed astronomy. They observed a pulsar in a binary system, a pulsar orbiting a white dwarf companion. By measuring the pulsar's timing variations, they could determine the white dwarf's mass and orbital characteristics. But there was something unusual. The pulsar and white dwarf were spiraling together. Their orbit was decaying. They were losing orbital energy. What was removing energy from the system? The answer: gravitational waves. The orbiting pulsar white dwarf system was producing ripples in space-time. These gravitational waves carried away orbital energy, causing the orbit to decay. For the first time, we had indirect evidence of gravitational waves, decades before direct detection with LIGO. This discovery was so significant that it earned a Nobel Prize, and it revealed something profound. Neutron stars in binary systems are laboratories for testing general relativity, quantum mechanics, and exotic physics. Scientists discovered that some neutron stars exhibit even more extreme behaviors. Magnetars, neutron stars with magnetic fields billions of times stronger than ordinary pulsars, spontaneously release tremendous energy. A single magnetar flare can release as much energy as our Sun produces in a year, all in a fraction of a second. In 2004, astronomers observed a magnetar flare so powerful it created a gamma-ray burst detectable across the galaxy. The energy release implied magnetic fields so intense they warp space-time itself. The magnetar's magnetic field energy exceeds the mass energy of mountains. Recent discoveries from 2022 to 2024 revealed neutron stars with even more exotic properties. Some appear to have crusts composed of exotic quark matter. Others show evidence of solid surfaces despite their incredible density. The internal structure of neutron stars remains incompletely understood. But this represents just one piece of a much larger puzzle hidden in neutron star behavior.
Scientists discovered that neutron stars don't always remain isolated. In binary systems, two neutron stars can orbit each other, spiraling inward over billions of years. When the neutron stars finally merge, something cataclysmic occurs. The merger releases gravitational waves so intense that LIGO detects them across the galaxy. The collision produces temperatures and pressures exceeding anything achievable on Earth. Exotic nuclear reactions occur. Gold, platinum, and other heavy elements are forged in incredible quantities. In August 2017, LIGO detected gravitational waves from merging neutron stars for the first time. The signal was different from black hole mergers, distinct because neutron stars produce electromagnetic radiation along gravitational waves. As the gravitational waves arrived at Earth, telescopes worldwide pointed towards the signal's source. For the first time, astronomers observed a neutron star merger across multiple wavelengths: gravitational waves, gamma rays, X-rays, visible light, and radio waves. The observations revealed something astonishing. The neutron star merger produced a gamma-ray burst, one of the universe's most violent explosions. The burst released as much energy in seconds as our Sun will emit in its entire 10 billion-year lifetime. Scientists discovered that the collision created a kilonova, an explosion powered by radioactive decay of freshly synthesized heavy elements. The kilonova glowed for weeks, gradually fading. Spectroscopic analysis revealed signatures of gold, platinum, and other elements previously uncertain to be created in such events. This single neutron-star merger solved a long-standing mystery. Where do the universe's heavy elements come from? For decades, astronomers debated whether neutron-star mergers, supernovae, or other events produced gold and platinum. The 2017 merger provided definitive evidence. Neutron-star collisions forge these elements. Recent observations from 2018 to 2024 tracked dozens more neutron-star mergers through gravitational waves. Each merger produces similar signatures: gravitational waves, gamma-ray bursts, kilonovae. Each collision confirms and refines our understanding of extreme physics. Scientists discovered that neutron-star mergers might merge into different final objects depending on the colliding star's masses. Two low-mass neutron stars might merge into a single, more massive neutron star. Higher-mass neutron stars might merge into a black hole. The transition between neutron star and black hole formation remains incompletely understood. In 2023, astronomers observed what might be the first definitive neutron-star black hole merger. The event produced gravitational waves distinct from neutron-star mergers, confirming that such collisions do occur in nature. The evidence extends beyond mergers into neutron atmospheres and surfaces. Some neutron stars appear to have solid crusts, regions where matter is so compressed that it forms crystal structures. These crusts can undergo starquakes, releasing enormous energy. The most disturbing evidence comes from observing neutron-star X-ray binaries, systems where neutron stars feed on companion star material. As material falls towards the neutron star, it heats to billions of degrees. The accretion disk around the neutron star glows intensely, outshining billion-star galaxies.
Neutron stars are laboratories where physics transforms. They're regions where ordinary matter ceases to behave normally, where nuclear forces dominate, where relativity becomes essential. The neutron star's crust is composed of exotic matter. At depths below the surface, matter transitions from relatively conventional nuclear material to phases that don't exist anywhere else in the universe. Neutrons form into exotic configurations called neutron drip lines, regions where additional neutrons are barely bound. Deeper still, in the neutron star's core, matter might transform into quark matter, a state where quarks, the fundamental particles comprising neutrons and protons, form a degenerate fluid. This phase remains theoretical. We've never directly observed quark matter, but neutron stars might contain it. This discovery forces us to reconsider fundamental assumptions about matter's nature. Under extreme conditions, matter transforms into forms with no terrestrial analogues. The physics governing neutron star interiors involves quantum mechanics, nuclear physics, general relativity, and quantum chromodynamics, the theory of strong nuclear forces, all operating simultaneously. Neutron stars also possess magnetic fields so extreme they challenge our understanding of electromagnetism. Ordinary magnets have fields of a few Tesla. Earth's magnetic field measures microtesla. Neutron star magnetic fields reach billions of Tesla, so intense they modify atoms' energy levels and affect light propagation. In magnetars, magnetic fields reach 10 to the 15 Gauss, quadrillions of Tesla. These fields are so intense they modify spacetime's geometry. Moving through a magnetar's field, charged particles experience distortions in spacetime that classical physics struggles to describe. Leading physicists recognize that neutron stars represent physics at its breaking point. Dr. James Latimer at Stony Brook University studies neutron star physics to understand matter under extreme conditions. Neutron stars are cosmic laboratories, he explains. They test every physical theory we have. They reveal the limits of our understanding. Dr. Anna Watts at the University of Amsterdam observes neutron star surfaces to decode their internal structure. By watching how a neutron star's surface oscillates after starquakes, we can infer the internal composition, she states. We are using neutron stars to map exotic matter phases. This forces us to reconsider fundamental assumptions about matter's nature. Ordinary matter seems stable and fixed, but under extreme pressure and density, it transforms into something alien. Neutron stars prove that matter's behavior depends profoundly on environmental conditions. The mystery of neutron stars will be solved through unprecedented observational capabilities and theoretical breakthroughs. The upcoming Einstein telescope, a next-generation gravitational wave detector currently in planning, will detect neutron star mergers with unprecedented sensitivity. This will reveal gravitational wave signatures hidden from current detectors, providing detail about neutron star internal structure. The Vera Rubin Observatory will survey the sky, detecting millions of transient events, including neutron star flares and magnetar outbursts. Each observation provides data about neutron physics. In 2024, the X-ray telescope Athena launched, designed to observe X-rays from neutron star systems with 5 to 10 times better resolution than current instruments. This will reveal accretion disk and magnetosphere details never before observed. Recent breakthroughs suggest we're approaching a watershed in neutron science. Advanced computational power now permits simulating neutron star mergers with realistic physics. These simulations reveal how extreme conditions produce heavy elements and predict gravitational wave patterns. Theoretical physicists have proposed that neutron stars might contain even more exotic matter than previously imagined. Kaon condensates, pion condensates, or color superconducting quark matter. Each phase represents physics beyond our current laboratory capabilities. In 2023, researchers proposed that some neutron stars might contain strange matter, a hypothetical phase composed of roughly equal numbers of up, down, and strange quarks. If strange matter exists and is more stable than ordinary nuclear matter, strange stars might comprise neutron cores. What technologies might help solve remaining mysteries? Gravitational wave detectors of unprecedented sensitivity, multi-messenger astronomy combining gravitational waves, electromagnetic radiation, and neutrino observations, advanced telescopes observing neutron surfaces in unprecedented detail. Predictions about future discoveries suggest several scenarios. Within a decade, we'll likely observe hundreds or thousands more neutron star mergers through gravitational waves. Each event reveals details about nuclear physics and element synthesis we can't obtain otherwise. Within 2 decades, we'll likely directly observe neutron surfaces with sufficient resolution to see features smaller than continents.
This will revolutionize our understanding of neutron structure and composition. Within a century, we might detect quark matter signatures definitively, proving that exotic matter phases exist in neutron cores. Recent breakthroughs suggest that life, if it somehow persisted on neutron surfaces, extraordinarily unlikely, would experience physics beyond our comprehension. Gravity so intense that falling 1 meter would accelerate you to nearly light speed. Magnetic fields that would tear apart molecules. Radiation that would vaporize any known form of life. What this means for us, for humanity, is profound. Neutron stars represent cosmic extremes. They're laboratories where physics breaks down and transforms. Understanding them is understanding matter's ultimate behavior under extreme conditions.
The most profound implications emerge when we consider what neutron stars reveal about reality itself. First, consider this. Neutron stars exist at the boundary between physics as we understand it and physics we don't yet comprehend. They're regions where general relativity, quantum mechanics, and nuclear physics all become essential simultaneously. Yet no complete theory describes all three together. Understanding neutron stars requires quantum gravity, a unified theory combining Einstein's relativity with quantum mechanics. Neutron stars are perhaps our best hope of observing quantum gravity effects, even indirectly. Second, neutron stars raise fundamental questions about matter's nature. What are matter's ultimate constituents? How do subatomic particles behave under extreme conditions? What limits exist on density and pressure? Neutron stars help answer these questions by providing cosmic examples of matter at extremes. Third, neutron stars connect to questions about the universe's future. If the universe's final state involves scattered neutron stars persisting for incomprehensible timescales, neutron stars help us understand the far future cosmos. Some speculative but scientifically grounded possibilities emerge. Scenario 1. Neutron stars harbor exotic matter. Neutron star cores might contain quark matter, strange matter, or phases of exotic matter we haven't imagined. These cores represent laboratories where physics transforms. Future observations might prove that entire new phases of matter exist in neutron star interiors. Scenario 2. Neutron stars are information stores. Perhaps neutron stars encode information in their structure. Perhaps the detailed mapping of neutron star surfaces reveals cosmic information stored as physical structure. Perhaps advanced civilizations use neutron stars as cosmic hard drives. Scenario 3. Neutron stars enable interstellar travel. Perhaps sufficiently advanced civilizations harness neutron stars' intense gravity and magnetic fields for propulsion or energy generation. Perhaps the extreme physics near neutron stars enables technologies we haven't imagined. Scenario 4. Neutron stars connect to black holes. Perhaps the boundary between neutron stars and black holes reveals something profound about quantum gravity. Perhaps observations of neutron star-black hole mergers will reveal how reality transitions between these extremes. Scenario 5. Neutron stars persist into the far future. Perhaps neutron stars survive even longer than black holes. Perhaps the universe's ultimate fate involves a cosmos populated by slowly cooling neutron stars persisting for timescales approaching infinity. The most mysterious aspect of neutron stars might be what they tell us about the limits of physics itself. In neutron star environments, our theories struggle. Our predictions sometimes fail. Our understanding becomes incomplete.
Perhaps neutron stars are telling us that deeper, more complete physics exists. Physics that unifies relativity and quantum mechanics. Physics that explains exotic matter phases. Physics that describes reality at the absolute extremes.
We began asking, what are neutron stars? How do they form? What do they tell us about physics? The evidence suggests something profound and deeply humbling. Neutron stars are real cosmic objects. We've observed them. We've detected them in mergers. We've measured their properties with stunning precision. They're among the universe's most extreme objects. What we've learned: neutron stars form from massive star deaths. They're city-sized objects weighing more than our Sun, compressed by gravity into alien configurations. They rotate at mind-bending speeds. Their magnetic fields are extraordinarily intense. They harbor exotic matter phases. They merge catastrophically, forging heavy elements and producing gravitational waves. What remains unknown? We don't fully understand neutron star internal structure. We don't know exactly what exotic matter comprises neutron cores. We don't fully comprehend the physics occurring in extreme conditions. We don't understand the complete relationship between neutron stars and black holes. The current scientific consensus acknowledges neutron stars as genuine astrophysical objects, matching predictions of stellar collapse and general relativity. Most physicists accept that quantum gravity effects likely occur in neutron star environments, but remain unobserved. Many recognize that neutron stars represent physics at its breaking point. Yet, this scientific consensus masks profound mysteries. Neutron stars might contain forms of matter we've never imagined. Their magnetic fields might enable physics we haven't discovered. Their gravitational environments might reveal quantum gravity's secrets. Neutron stars represent matter under extreme compression. They're what remains when massive stars die violently. They're cosmic laboratories where physics transforms into something alien and beautiful. We inhabit a universe that contains these extreme objects. Neutron stars exist by the thousands throughout our galaxy. Each one is a cosmic monument to gravity's power. Each one tests the limits of our physics. Each one challenges our understanding of reality's nature. Neutron stars are reminders that the universe is far stranger than our everyday experience suggests. They're evidence that matter can be transformed into forms with no terrestrial analogues. They're proof that physics under extreme conditions becomes exotic and beautiful. The universe contains these cosmic extreme physics laboratories waiting to be understood. And with each observation, each merger detection, each gravitational wave arrival, we learn more about matter's true nature and reality's deepest principles. So, there you have it. Neutron stars, the universe's densest objects where matter gets crushed into forms we can barely comprehend. Here's what absolutely fascinates me. We can measure a neutron star's properties from light years away. We can watch them rotate hundreds of times per second. We can detect them colliding and merging. We can observe the heavy elements they forge. All of this is real. All of this is happening right now in our galaxy. But here's what keeps me up at night. Neutron stars are still largely mysterious. We don't fully understand what's happening inside them. We don't know exactly what exotic matter comprises their cores. We might be missing entire phases of matter that exist nowhere else in the universe. And when you realize that neutron stars represent the densest objects short of black holes, when you realize that physics completely transforms in these environments, it puts into perspective how little we actually understand about reality. If you want to explore more cosmic extremes, from black holes to the multiverse to the deepest mysteries of physics, please hit that subscribe button. We dive into topics like this all the time.
Drop a like and let me know in the comments what aspect of neutron stars amazes you most. Their density, their rotation, the killer novae from mergers, and what cosmic mysteries should we explore next? Thank you so much for watching. Keep asking questions about the universe's extremes. Keep marveling at what physics permits, and remember, the cosmos is far stranger and far more wonderful than we imagine. Until next time, I'm JJ Littleton. Thanks for joining me on this journey to the universe's densest objects.